Good evening. What a pleasure to be present at this Mullen event. A wonderful family and a great tradition, apparently, of these lectures. And I'm honored to be chosen to be one of the speakers. Tonight I thought we could take up a question that has some interesting ramifications. We can discuss the question and perhaps the answer, or a preferred answer, and then see where it leads, where that kind of reasoning leads. So I spent a good deal of my life, years ago, studying the elementary particles. They're the fundamental building blocks of all matter everywhere in the universe. And each elementary particle, each kind of elementary particle, is the same wherever it's found. All the electrons in the universe are identical, and so on. The properties of these elementary particles are intimately connected with the fundamental forces of nature. And so far, through observation, we have four such forces. But we believe, we theoreticians believe there must be many more, and probably even an infinite number, progressively associated with progressively smaller and smaller distances and higher energies. That's why the ones associated with very small distances and very high energies we haven't seen yet, but we will in the future, probably. Meantime, we're familiar with four of them. Gravitation, which has been known and somewhat understood since Isaac Newton's time. We'll talk a lot about Isaac Newton tonight. Electromagnetism, which was just beautifully described in the 19th century by the Scottish scientist James Clerk Maxwell. And then the strong force, which is what holds the nuclei of the atoms together. And finally, the weak force, which is responsible for beta decay and various other kinds of radioactive decays. But as I said, there must be many more. We know these because the gravitational and electromagnetic forces go like, as you know, they go like 1 over the distance squared. So they're present out to very, very, very large distances, important out to very, very large distances. The strong force is a short-range force, but its range is reasonably large. The weak force, a little bit shorter distances. And at still shorter distances and still higher energies, one will undoubtedly run into many more forces. Now, what I want to start with tonight is this remarkable observation that in this field of fundamental physics, that is, what matter is made of if you chop it up very small, a beautiful or elegant theory is more likely to be right than a theory that is not beautiful or elegant. Recently, a biography has appeared of Paul Dirac, who's a very great elementary particle physicist. Spent most of his life in Cambridge, England. And Paul Dirac was a particular devotee of proclaiming this, that in looking for the right theory, look for the beautiful one. Here's an example that involves my personal experience. In 1957, which is now some years ago, what is it, 52 years ago? Is that possible? Anyway, some of us put forward a long time ago a partial theory of the weak force. And we put it forward despite the fact that we had checked it against 7 different, quite important experiments, and it disagreed with every single one. But it was a beautiful theory. It was very beautiful. And we published it anyway. And we said in the article that we didn't care that it was a disagreement with 7 important experiments. The experiments must be wrong. And they were, every single one of them. Einstein, Albert Einstein, when he put forward special relativity in 1905, was faced with a lot of skepticism. People wondered whether it was right, and they attacked it, and so on and so on. And then, in the midst of all that, some experimentalists reported that maybe they had found some deviations from Einstein's special relativistic theory. And people came up to him and asked him, what about that? Are you worried about these apparent violations of special relativity? And Einstein said, not at all. The theory is so beautiful, it must be right. I don't believe in these experiments that challenge it. And he was completely right. Those experiments that challenge special relativity were just mistakes. As it says here, he was convinced that a really beautiful theory would survive, and contrary experimental results would prove to be incorrect, and they really were. Now, we have to reflect on this. First of all, what do we mean by beauty and elegance? Second, why should it work? Why on earth should beauty or elegance, as we humans perceive it, have anything to do with the correctness of a fundamental physical theory that describes the behavior of all matter in the universe? And what have human beings got to do with it? Does it somehow depend on human beings and their special properties and what human beings have evolved to do and what human beings have learned? Or is it something deeper having to do with nature? A theory appears beautiful or elegant, in my opinion, when it's simple. In other words, when it can be expressed very concisely in terms of mathematics that we've already learned for some of the reasons. Now here, let me describe some of the ideas from which I start in discussing this interesting intellectual puzzle. One of them is that there really are laws of nature. Nature actually obeys laws. And to quote Newton, it is the business of natural philosophy to find them out. Natural philosophy, of course, is what science was called in the 17th century. Natural philosophy was distinguished, if you like, from armchair philosophy, where you stated things about nature that you believed must be true without looking. Natural philosophy, or science, involved actually looking to see what was true. And it received this special new name, natural philosophy. And nowadays we call it science. So the business of science is to find out these laws of nature. And the point of view from which I will be starting is that these laws are not just created by the human mind, although human beings are trying to find by successive approximations what these laws are, at least to get closer and closer to them, maybe someday actually to write them down. These days, science is under attack, as all of you know, from two different directions. One is from people who want to misstate the results of science or suppress the results of scientific investigation because they have political agendas that seem to be endangered by new scientific knowledge. That's one thing. The other threat to science comes from the opposite pole, from within the universities, where in certain departments, in certain universities, there is a growth of a certain sort of post-processual thinking. As I say here in this slide, I call it post-rational or post-intelligent. And these people, some of them, preach that science is just a construct of the human mind. Some of these people seem to believe that one scientific theory wins out over competing scientific theories because the person proposing the theory is more powerful than the others who are proposing the contrary theory. Well, that can happen. There are lots of abuses of science every once in a while. They're rare, but they occur. The point is that science is a self-regulating enterprise because it keeps appealing to nature. It keeps asking people to look at what actually happens in nature. And therefore, science is, in the long run, proof against these abuses of science, which in any case are rare. They do exist, though. Now, as you've all heard, elementary particle theorists have been trying for years and years and years to find a deep, unifying theory, a fundamental theory of all of the elementary particles and all the forces of nature, an overriding, unified quantum theory of all the forces and all the particles. We don't know whether that will be possible in the future, especially in the near future, but people are working on it, and in many circles it's believed that perhaps it's getting closer. We know what this theory would have to be like, roughly speaking. It must be quantum mechanical. Now, in quantum mechanics, something very important occurs. It has to do with uncertainty and ignorance and randomness and lack of certainty in general. Usually that comes from simple ignorance. That is, the universe consists of a huge, huge volume in which all kinds of things are going on. Distant galaxies, distant stars, planets, and so on, through an enormous universe. And most of that we don't know much about. Even here, we don't know much about things. We don't know things deep in the earth. We don't know things down to very small distances. We don't know things that have not been measured, and so on and so on. There's a vast amount of ignorance. And that vast amount of ignorance gives rise to a huge amount of uncertainty. But in quantum mechanics, that's not the only source. In addition to that, in quantum mechanics, there's a huge amount of random stuff that's genuinely random. It isn't just that we don't know it, it's that it actually occurs by chance. That's therefore, quantum mechanical theory does not accurately predict the future. Even if you know everything, it doesn't accurately predict the future. What it predicts is probabilities for future events given the fundamental laws of nature and the past events. In quantum mechanics, you have branching histories. History continues, and then it gets to a chance event which can come out different ways, and all those different ways that the event can come out are branches. And then on each branch, the same thing happens. There's another random event, another chance event, and it can go several different ways. And depending on which way it goes, you have a branching again. And so you have branching after branching after branching, a tree which constantly branches more and more and more and more as you go into the future. That's the kind of prediction that quantum mechanics can make. And at each branching, there are probabilities. Quantum mechanics can give probabilities for the different branches, the different alternative results of the chance event that's involved. Now, sometimes those probabilities can be very close to 1 or 0, in which case you are essentially making an exact prediction. But in many cases, not. In many cases, the probabilities vary a lot and don't concentrate around 0 and 1. In that case, there is genuine, fundamental ignorance. Not ignorance that comes just from not knowing what's going on, but fundamental ignorance about the future because it's undetermined. For example, suppose you take a nucleus of an atom that is disintegrating and emitting what's called an alpha particle. That's a helium nucleus. The alpha particle comes out. In what direction does it come out? All directions are equally probable. You cannot predict before the nucleus emits this alpha particle in what direction it will go. It's fundamentally unknowable until it happens. So that's peculiar to quantum mechanics. That's not the kind of thing that happens in classical physics. But quantum mechanics is correct. So the result is that the history of the universe is co-determined by 3 things: the fundamental laws of the elementary particles and the forces, maybe someday a unified quantum theory of all the particles and all the forces, this ideal, long-sought, unified theory. That's one. That's number 1. Number 2 is an unimaginably long sequence of chance events, which can come out different ways. Accidents, I call them. And third, there's the initial condition of the universe at the time of what a lot of people call the Big Bang. I don't like that name because it was an insult invented by people who didn't believe in the Big Bang. But let's use it anyway, because the people in the press, with their annoying habits, have imposed this on us now. So let's call it the Big Bang. But anyway, we have three things then. The initial condition, the Big Bang, the fundamental laws, and all of these chance events that have occurred throughout history with predictions possible only probabilistically. Now here I should make a remark. The press, with its annoying habits, constantly talks about a theory of everything. That's this fundamental theory of all the particles and all the forces that we hope will be available someday. They call it a theory of everything, but it would not be a theory of everything. Even if we found it tomorrow, it would not be a theory of everything, because it doesn't include the initial condition, the Big Bang, and it doesn't include all these chance events, which constitute an enormous body of information. Now, when we look at science, we see that the sciences other than elementary particle physics and cosmology depend on these chance events. Elementary particle physics and cosmology are presumably fundamental and occupy and describe the whole universe. But they describe histories that are branching. And the results of these branching histories are an extra set of important pieces of information. They are not contained in the fundamental laws, and they're not contained in the initial condition. They're extra. And they are chance events, predictable only probabilistically, and an unimaginably large number of them. And most of science depends on those as well as on the initial condition and the fundamental laws. For example, chemistry. Chemistry is essentially derivable from physics, but not completely, because chemistry is there only when you have the temperatures and pressures present that allow atoms and molecules to exist. If you're at too high a temperature for atoms and molecules, and they're stripped of their electrons, you don't have chemistry anymore. You still have physics, but you don't have chemistry. To have biology, you need the accidents that led to life on Earth. And since we don't know all about those, there's a huge amount of ignorance associated with the life sciences. And then since then, there have been all the accidents of evolution. Evolution, governed in part by natural selection, is, of course, very important. But it leaves unsaid all sorts of accidental things that have happened in the course of evolution, and so on and so forth. So the fundamental theory co-determines the history of the universe along with the initial condition and all of these accidents, all of these chance events. Therefore, the basic laws cannot possibly, should not be called a theory of everything. And of course, the press will continue to do so. Now, physicists, in their search for information about this unified fundamental theory that everybody would like to see, it's a sort of holy grail of elementary particle physics. In the search for that, what happens is that we work our way from shorter to shorter and shorter and shorter distances by having accelerators, particle accelerators, that reach higher and higher and higher momenta. In other words, higher and higher and higher energies. So as we build these accelerators at vast expense, now there's only one near Geneva in Switzerland, which unfortunately suffered some accidents, but it will turn back on in a few days. As we build these machines, we are accelerating particles to higher and higher energies, and therefore investigating shorter and shorter distances. And as we do that, we learn more and more and more about the laws. We get closer and closer to the center. We get higher and higher in energy. And that's been compared sometimes to peeling the skins of an onion. Now, here's where we get to my proposal. This is what I suggest as the explanation, if you like, of why simplicity or elegance is a successful criterion in choosing a correct fundamental theory in physics. The reason is that the reason I claim is that as we go to higher and higher energies or smaller and smaller distances and build more and more expensive accelerators and so on and get them to operate, we notice that the manifestation of the fundamental law at that scale of distance or energy resembles the previous one at the slightly lower energy or the slightly larger distance. In other words, as we go to smaller and smaller distances and we go to higher and higher energies, the manifestations of the fundamental law resemble the previous manifestations. Approximately. There is an approximate self-similarity. Isaac Newton talked about this, amazingly, in the 17th century. He called it nature conformable to herself. That the manifestations of the fundamental law at different scales of distance or energy approximately resemble one another. So when we encounter new phenomena by going to shorter distances or higher energies, they are naturally described in a way that's related to the phenomena that we already know about and for which we already have mathematics. So the new mathematics necessary to describe the new discoveries at higher energies or shorter distances will resemble the mathematics we had last year or last decade or last century for describing the longer distances and the lower energies. As a result, newly encountered phenomena are described rather simply and therefore elegantly in terms of math close to what was already developed for the phenomena, the longer distances and the smaller energies. So here's a trivial example. Newton found that gravitational force goes like 1 over the distance squared. Everybody's learned that in elementary science and school. 100 years later, or more, Coulomb in France discovered the formula for the electrical force between two electric charges. Same formula, 1 over the distance squared. There's a trivial example of what I was just saying. You go deeper, you study electromagnetism instead of just gravitation, and you find the same law. Again, the inverse square law. Later on, James Clerk Maxwell combined the equations for electricity and for magnetism into a single set of equations for what's called electromagnetism. Remarkable achievement. And it again brought together two apparently disparate phenomena in the same discussion, the same set of formulae. Now we have to talk about symmetry. What do we mean by symmetry? In math or in physics or in other subjects like that, we mean what kind of operations leave the object alone. For example, a circle, if you rotate it around the center of the circle, stays the same. So the circle is said to be invariant under rotations about the center. You rotate it around the center, it doesn't change. So an object or a phenomenon is said to exhibit a certain kind of symmetry if performing those symmetry operations consistently leaves the description unchanged. That's clearly what happens to a circle when you rotate it around the center. We say the object is symmetrical then. Maxwell's equations for electromagnetism are symmetrical, that is, they keep the same form when you rotate space. They don't depend on a particular direction in space. There is no preferred direction in space for electromagnetic phenomena unless you have you're given some magnetic field or something of that kind. But if you're not, you just have empty space and you put in electromagnetic phenomena. They are perfectly symmetrical under all rotations. When that's true, you can write the formulae in a more concise way, exploiting this simplicity, exploiting this symmetry. That way of writing was called vector analysis. It was developed in England and at Yale in the United States. Now, Einstein's special theory of relativity consists of the following. It's not usually stated that way, but this is what it is. You look at the symmetries of the Maxwell equations for electromagnetism, and you apply those symmetries more broadly. You apply them to mechanics as well as to electromagnetism. That's special relativity. That was Einstein's brilliant idea. It's not how he would have described it exactly, but that's a good way to talk about it. He took the symmetries of electromagnetism and he generalized them by applying them to mechanics as well as electromagnetism. But at the same time, because the electromagnetic equations are symmetrical under Einstein's transformations, they can be written more simply again. Well, here's what they look like. You don't have to understand them, you just have to look at them, enjoy them as an artistic manifestation. Here are the equations of electromagnetism the way Maxwell would have written them at the beginning, in terms of an x direction, a y direction, and a z direction. X, y, z, something like that. So there are all these components of the electric force and components of the magnetic force, and here are the currents and here are the charges. The charges and currents generate all these electric and magnetic phenomena. Now, when you take account of the rotational symmetry of this system, you can write it in a much simpler way, like this. This is the way it's written in the notation of vector analysis, as developed, for example, at Yale, my old school. Now, when you do special relativity, you're putting in even more symmetry. You're putting in the symmetry of the entire symmetry of Maxwell's equations, then they're reduced to just two equations. Here they are. Now, whoever drew up this slide, I guess it was my wonderful assistant, Laurie, cheated by making these smaller in print than these. So when I say these equations are are shorter and simpler, she's cheated a bit just by making them the formulae smaller. But even if you bring the quantities up to the same size as here, you see that it is a simpler manifestation. And the same when we go from here to here. You're finally left with only two equations. One of them says the charges and currents generate the fields. That's what this says. And this one says there is no single magnetic pole. Magnetism arises entirely from the motion of electric charges. Now, that may not be 100% true. In the long run, when we look at the universe and the whole history of the universe, there might be some exceptions to that. But for all we know today, it's true that there are no single magnetic poles, and that's what this equation says. Now, what about the strong and the weak interaction? What do we do about those? Well, 50 some odd years ago, it's now about 55 years ago, a wonderful Chinese-American theorist called Yang Zhenning, whom we knew as Frank Yang, and Robert Mills, an associate, a young associate, put forward a generalized set of equations. They look like Maxwell's equations with an extra term, and they reflect a higher symmetry. There's an entirely new symmetry in the theory. But it's a generalization, a mathematical generalization of Maxwell's equations for electromagnetism. And what does it describe? They didn't know. They just wrote a paper saying, here is a very beautiful looking generalization of Maxwell's equations with a higher symmetry. Look at it. Isn't it beautiful? Like electromagnetism, it is a so-called gauge theory. Gauge theory is one in which the symmetry of the equations dictates the form of the equations. So once you know the symmetry, you actually know the theory. Gauge theories are magical. They have magical properties. Well, Yang and Mills wrote down this theory, and that's it. They gave it to us. They didn't say what it was good for. It was just generated for its beauty alone. It was a beautiful, simple generalization of Maxwell's equations for electromagnetism. But over the next few years, some of us showed how to generalize it further by widening the symmetry in the theory. And we found there were various possible widenings. Next, we showed that it was the right theory for the strong interactions, miraculously. They just wrote it down as a beautiful generalization of Maxwell's equations for electromagnetism. And lo and behold, when it was slightly further generalized by some of us, it became the correct theory of the strong interaction. It's called, I named it, quantum chromodynamics. Chromodynamics because there's a quantum number in there that we named color as a joke. It's a three-valued variable, and we called it red, blue, and green, just as a joke. So the theory based on it is called chromodynamics. And it turns out, as far as we can tell, to be the correct theory of the strong interaction, the interaction that holds the atomic nucleus together. This was a great dream for decades to find the law of the strong interaction, and it came for almost nothing. Yang and Mills generalized Maxwell's equations, and we slightly generalized Yang and Mills' equation, and there it was, the theory of the strong interaction. Amazing. Beauty giving rise to truth. And the reason is that nature is self-similar. When you go from the scale of electromagnetism to higher energies and shorter distances, and you start investigating the short-range force that comes from the strong interaction, you find a similar situation to what you had before at the lower energies and the longer distances. Nature is self-similar, approximately, as you go from scale to scale. It exhibits, it's conformable to her, nature is conformable to herself as you go from scale to scale, approximately. So, I think we have accounted for why beauty and elegance are useful criteria for finding the next theory. Here's what Newton said. The attractions of gravity, magnetism, and electricity reach to very sensible distances, and so have been observed by vulgar eyes. And there may be others which reach to so small distances as hitherto escape observation. In other words, he was predicting the strong force, the weak force, and so on. Amazing. And perhaps electrical attraction may reach to such small distances even without being excited by friction. Isn't that wonderful? We know now that electromagnetism persists down to very, very small distances, the same laws. And what they knew about electricity then was that if you rubbed glass on cat's fur, you would get a spark. Now we know a hell of a lot more about electricity and magnetism than that. And Newton foresaw that. He was amazing. We assumed there was a basic unified theory, which has not yet been found, but we know something about what its properties must be. We talked about steps toward unification, like unifying electricity and magnetism, maybe unifying all the forces if we're lucky someday. We talked about symmetry and how it can make the description of something much shorter and simpler, and also how in gauge theories, the symmetry actually determines the theory. So once you learn the symmetry, you know the form of the theory, which is amazing. Finally, the main thing that we were emphasizing tonight, which is that apparently nature exhibits approximate self-similarity across scales of distance or energy. And that's the reason why a simple-looking or beautiful-looking theory is more likely to be correct than one that isn't. Now, gravity was fairly well described already in the 17th century by Newton, long before Maxwell in the 19th century wrote his equations for electromagnetism. Historians of science still argue whether Newton saw an apple falling from a tree on his mother's farm, and that persuaded him that the force that caused the apple to fall toward the earth was similar in form, in fact was identical in form, to the gravitational force that made the moon be attracted by the earth and go around in its orbit, and so on and so on. Newton wrote about that, and here's what he wrote. Nature is very consonant and conformable to herself. That's in one place. In another place he wrote, and if nature be most simple and fully consonant to herself, she observes the same method in regulating the motions of smaller bodies, which she doth in regulating those of the greater. This principle of nature being very remote from the conception of philosophers, in other words, of scientists, I forbore to describe it in that book, that's Principia Mathematica. I forbore to describe it in that book, lest I should be accounted an extravagant freak, and so prejudice my readers against all those things which were the main design of the book. So he had never dared to say it before, but this was what was in his mind. And he was applying it here to something very simple, namely that the 1 over r squared law that he postulated for the moon and the planets and the earth and so on was the same as the law that caused the apple to fall down toward the ground in his mother's orchard. What happened was they had the plague in England, and in particular they had the plague in Cambridge in 1665, and school was out because of the plague. We haven't done that with the swine flu, but people have talked about it. There we had the plague. Cambridge was closed. They sent everybody home. And he went to his mother's farm in Lincolnshire, and some people claim he saw the apple falling from the tree and said, aha, my moment of illumination. That force that caused that is the same as the force that makes the moon go around the earth, and so on. And he was right. It is. But this was a very, very simple example of what we're talking about, that nature is self-similar on different scales. Here it was just that the 1 over r squared law applies at big distances and also at small distances. It's a very elementary example of what we're talking about, but that was the first thing that Newton thought about in connection with it. Now, nobody could possibly claim this as a property of the human mind. The 1 over r squared law holds at large distances and small distances. We know it does. It's perfectly reasonable that it does. And it's clearly an inherent property of gravitation. It has nothing to do with the human mind. Any intelligent thing anywhere in the universe would come to the same conclusion because it's a real fact about the world. Even if that thing that was making the investigation had 7 eyes and 6 tentacles and a brain shaped like a pretzel, it wouldn't make any difference. That intelligent thing would still reach the same conclusion because it's a property of the law of nature. In this case, a property of gravitation, and a very simple property. Now, as many of you know, some year around then, 1665, 1666, has been referred to as an annus mirabilis, a marvelous year. And really, during that year or two, Newton worked on a few things. So those of you who are research students can think about emulating Newton here. He had this time off, and he improved the shining hour by doing a few things. He worked on the theory of gravitation. He worked on Newton's laws of motion. He worked on the calculus. And he showed experimentally that white light was made up of all the colors of the spectrum by refracting white light through a prism. As my second wife used to say, she was a poet, and she had a lot of nice things to say. She said, he could have written quite an essay on what I did over the summer holidays. Think about it. The laws of motion, gravitation, the calculus, and showing that white light was made up of the colors of the spectrum. And actually, he did a few other things, too. But one thing he did was to appreciate nature conformable to herself. So the conformability of nature to herself is a consequence of the nature of the fundamental law, that long-sought unified theory. Has that property. It's a law of nature, and it has that property. The applicability of the criterion of simplicity or beauty follows from that, as we saw. Finally, there's another thing that people have discussed. Eugene Wigner, a very great theoretical physicist, who shared one of these Swedish prizes that people make such a fuss about. Eugene wrote a paper on what he called the unreasonable effectiveness of mathematics. Why in fundamental physics does mathematics play such a good role? Why do we keep using mathematics successfully? What's so great about it? Well, you see, from our point of view that we're developing here tonight, it must be that it's the fundamental theory. It's the fundamental underlying theory that is naturally expressed in a certain kind of math, and that kind of math is, of course, very effective, because it's the kind of math in which you naturally express this theory, the theory that actually describes the world. So these three different things that people have noticed, that philosophers of science have noticed, don't have to be considered to be separate metaphysical postulates. They all follow from the fundamental laws of physics. They are what you call emergent properties. What is emergence? Emergence means that some phenomenon of a certain kind comes out of more fundamental understanding of nature at a more fundamental level, and looks different. It looks different. It comes out of the underlying principles, but it looks like a new set of laws. For example, the chemical bond. Chemical bond comes from the laws of electromagnetism plus quantum mechanics, and it's fairly straightforward. But you don't see, when you announce Coulomb's law and you announce quantum mechanics, you don't see immediately that it's going to lead to a chemical bond. You have to do an awful lot of work to do that, to show that. But the chemical bond emerges, and it's an interesting concept in its own right. And chemists naturally talk about it. They don't keep going back to the explanation from fundamental physics. They treat the chemical bond as a thing in itself at the level of chemistry. The cell in biology is something like that too. You don't say the cell is just a bunch of physical forces and chemical elements and so on and so on. It has a whole set of rules of its own. They emerge from physics and chemistry plus accidents. Physics and chemistry plus the results of chance events. But that's all. They look like a whole new layer of learning, a whole new kind of science. The same with geology. Geology emerges from chance events in the history of the earth and important principles about rocks and so on that come from physics. So it's a combination of the fundamental laws of physics and a whole lot of chance events that give rise to geology. Now, in practice, you don't reduce things. Reduction is possible. Reduction of each of these sciences to a more fundamental level is possible in principle, provided you add in all the necessary accidents, the fundamental laws plus accidents. But it's not a wise way to approach it. You do not treat earthquakes in terms of quarks. Doesn't make any sense. When you talk about earthquakes, you talk about rocks and you talk about the vibrations of the earth and so on and so on. You do not go all the way back to quarks. There's no need to and there's no reason to. So there's a whole new phenomena arise at a new level which depend on the underlying laws and accidents and look new, and they are worth treating on their own as rules of geology, rules of biology, rules of astronomy, and so on and so on and so forth, even though they arise ultimately from the fundamental laws of physics plus accidents, and in principle they could be reduced. But in practice, that's not a very good strategy for studying nature. So here I say this: doesn't life on Earth somehow involve more than physics and chemistry plus the results of chance events and so on? No, it doesn't. At least I don't think so. How about mind? That's the last refuge of obscurantism, consciousness. What about mind, consciousness, self-awareness? I think it just comes from neurobiology plus the accidents of primate evolution. I don't believe there has to be something more. But this fact that you can get something more without having something more is the essence of the idea of emergence. It's not necessary, I think, to assume additional mechanisms or hidden causes. Maybe there are additional mechanisms or hidden causes, but I don't think it's necessary, logically necessary, to have them. And once emergence is considered, a huge burden is lifted from the inquiring mind, because we don't need something more in order to get something more. And here we've said this already. Reductionism is not wrong, but it becomes impractical. So this is the last thing I want to say. It doesn't diminish the importance of the chemical bond to know that it arises from electromagnetism and quantum mechanics and accidents. It doesn't diminish the significance of life on Earth to know that it emerged from physics and chemistry and accidents. It doesn't detract from the achievements of the human race, including the triumphs of the human intellect and the glorious works of art that have been produced for tens of thousands of years, to know that our intelligence and self-awareness, greater apparently than those of the other animals, have emerged from the laws of biology plus the specific accidents of hominid evolution. We can still celebrate all these wonderful, miraculous-seeming things while acknowledging that probably they are the products of emergence. Thank you.
I've read one theory that talks about time as not being continuous, but being a discrete entity. Do you have any thoughts on that?
Well, it's a very useful thing in coarse graining quantum mechanical histories of the universe. Jim Hartle and I base our whole approach to quantum mechanics on coarse-grained alternative histories of the universe that decohere from one another. And they have to be coarse-grained in order to decohere. In order for the interference terms between histories to be washed out, you have to have coarse graining. Now, what does this coarse graining consist of? Well, in practical cases, it consists of several things, the first of which is to replace continuous time approximately by discrete instance of time at some separation, some small, very small separation. Besides that, you also use only certain variables, and those variables are integrated over small volumes of space, not points in space, but small volumes, and so on. So there are various elements to this coarse graining procedure that we recommend. But the first one is to make the approximation of replacing continuous time with discrete time. That doesn't mean that time is really discrete. Might be, but that's not what we mean. We just mean that coarse graining the situation by approximating time by discrete intervals is a good idea. Does that help your question?
No.
No. What was your question?
I'm only kidding.
What was your question?
Well, it seems that there's a fundamental philosophical issue of a non-continuous time.
Yes, well, that's what I said. Maybe time is really non-continuous. That's possible, but that's not what we do. We just approximate it by a non-continuous time.
When you were discussing quantum mechanics, you mentioned the idea of branching probabilities. Do you feel that there's any value in discussing whether or not there are multiple universes defined by the branching probabilities versus a single universe?
Well, yes, that's a very interesting question. You can, if you like, associate some world with every branch. I mean, that's a lot of worlds, right? Because the branches branch and then branch some more and branch and branch and branch and branch over little tiny intervals of time for 10 to the 10th years. That's a lot of stuff. You can do it, though, if you want, and say there's a world for every one of those. But what you gain from it, I can't imagine. Why not just talk about many histories of one world? Now, there's another possibility, namely that actually we live not in a universe, but in a multiverse, which is like a universe that has spun off little baby universes. That's a different story. In that case, you have universes that are not independent. These universes have a common origin, and so they're correlated with one another. And the quantum state is a, what shall I call it, not a pure state, but the opposite of I forget what the word is, the opposite of a pure state in quantum mechanics. Because the different pieces, the different sub-universes have been in contact with one another. In that case, you ought to include them, because they add something to the story. But if the different so-called worlds are all independent, and each one is associated with a different history, why bother? Why not just call them different histories? Why bother to make up some fictitious world for each one? You can do it if you like, but I don't think it adds much.
What's your opinion about string theory?
Well, I'm a patron of string theory. As a conservationist, a dedicated conservationist, I set up a nature reserve for endangered string theorists at Caltech. And between 1972 and 1984, many of the important results in string theory were obtained by my group. Not by me, I didn't do it, but the people that I brought to Caltech. And I believed, and I still believe to some extent, that string theory may help in the approach to finding this underlying unified theory that we all hope for. But a number of complications have arisen on the way. And so we're not there yet. We're not close to it yet. But I wouldn't be surprised if superstring theory helps us in the search for that theory.
Can I follow up?
It has the following very distinct positive feature, that it predicts general relativity, general relativistic gravitation a la Einstein. Predicts it. And it predicts it within quantum mechanics, and without encountering any of the crazy infinite corrections that plague other attempts to unify general relativity with quantum mechanics. So it has some very distinct advantages.
So does it pass
but whether it will really lead us to the underlying unified theory, nobody knows.
But does it pass your elegance criteria?
Yes, it does, very much so.
There's talk out there that many of the constants that determine how the universe is structured these days are sort of arbitrary, and if they had slightly larger values or slightly smaller values, they would be, the universe as we know it wouldn't exist. And so sort of a corollary of that is that the universe that we're in is the one that we're in because we can observe it. Is this sort of part of is this an accident, one of the accidents that you're talking about?
Well, it is certainly one of the things I'm talking about. Whether this way of looking at it is correct, I don't know. It may be. I haven't really come to terms with it myself so far, with this type of argument. It says that maybe a universe in which observers like us could exist depends sensitively on values of certain fundamental constants. The second point that is made, as you said, is that maybe those constants are actually treated as accidents in the theory. That is, accidents that occur right away at the beginning of the expansion. Maybe. And then if that's true, then maybe the reason that they have these values that just work, just manage to work, is that if they didn't, there wouldn't be anybody here to write about it. Now, that kind of argument is strange. I have never known exactly what to make of it, but it's interesting. It may be right.
Do you think the time will ever come to pass where science will trump ideology? And if yes, under what circumstances?
What kind of ideology do you have in mind?
I don't have one in mind. Just the
Dalai Lama says, when faith and science collide, science trumps faith. But that's the Dalai Lama.
What do you think?
I just spent a few days with him. He's a wonderful person. But I think that ideology is important and is unlikely to be swallowed up by science. I think that the reverse is happening in some places, that ideology is swallowing science. We know about that. We went through some years of that in this country recently.
At the risk of expulsion from your fictional thugs, I want to ask you, what has been the impact on your thinking of religion, history, and nationalism? And no one-word answer is permitted.
Oh, well, let's see. Nationalism is an example of what you can call generalized tribalism. That is, our tendency as a species to divide up into little groups that don't get along with one another. Now, as history has gotten along, these groups have gotten larger and larger in many cases. So, for example, the whole of Western Europe is now a place where we would not forecast a war very soon, even though we and our parents have lived through 2 gigantic wars in Western Europe. Nowadays, it would be considered very improbable because the people of Western Europe have become we, rather than we and they, to a considerable extent. Not entirely, but to a considerable extent. So that's a very important issue, whether in the future we will be able to bring this force under control, this force favoring fission, favoring conflict, and so on and so on. It's very critical. As to religion, that's another thing that causes a great deal of trouble in the world, a huge amount of enmity and so on, along with many very good things. Beautiful art, feelings of comfort, facing death more easily in some religions, and so on and so forth. So religion has many positive consequences and many negative ones. But of course, in many cases it requires believing in the supernatural. So in that sense, it's to some extent, in some respects it can be opposed to science. Not always. Frequently, in some religions, people don't create a conflict with science. As I mentioned, for the Dalai Lama, he doesn't.
Yeah. Thank you.
But I don't have any general wisdom to dispense on this subject. It's not my specialty. Around here, I understand there are many specialists on religion, and it would be better to call on them rather than on me to discuss it. Thank you.